Hello, welcome to the Oxford Discrete Maths and Probability Seminar. So this week it's a real pleasure to have Paul Bastide, who's going to talk on skipless chain decompositions and improved poset saturation bounds. Thanks, Paul.
Thanks a lot for the invitation. Thanks, Alex, for the introduction. So yeah, I will talk about skipless chain decomposition. And this is based on two joint work with, the first one is with Carla, Hugo and Tom, and the second one is with Carla, Maria and Tom, without Hugo this time. Okay, so let's jump into it. Maybe the first ground set for all this talk would be the Boolean lattice. So it's just the set of all subset of 1 up to n, and ordered by the relation inclusion, and we see it as a poset, so just a partially ordered set. And for example, on the right, you can see the Boolean lattice of dimension 3. It's often represented like this as a poset, which is called the Haas diagram, where roughly it's just the a graph that represents the relation, and that's kind of minimal in the sense that you don't put edges that are implied by the transitivity. For example, the empty set is included in 1, 2, but we don't put the edges because it's already included in 1, and 1 is included in 1, 2. Okay, so I will always represent poset like this during this talk. And yeah, in general, I will also forget the direction on the edges and always consider that the edges go upwards. Okay, that's usual thing. Okay, perfect. Maybe some very basic definition on poset that you probably all know. A chain in a poset is just a set of elements where each are pairwise comparable, and an antichain is the opposite. It's a set of elements that are each pairwise incomparable. But now maybe some definition that is a bit more specific to this talk. We say that the chain is skipless when roughly there is no gap in the chain. What I mean by it, so on the side you see some non-skipless chain, because there is a skip, is that you cannot find some element x in your posets that you could put in between two elements of your chain. So for example, here 1, 2 could have been put in between 1, 2, 3, and 1. So this chain would have been skipless, but the first one was not skipless. And mind that it does not mean that the chain is maximal. For example, the chain 0, 1, 1, 2 is also considered skipless, even though it could be maximal if it contains also 1, 2, 3. Okay, I hope this definition is clear. Of course, you can interrupt me at any time if you have question on the definition. I hope it's clear because it will be useful for the rest of the talk. Right? Okay, so one, I guess the most well-known theorem on posets is by Dilworth in the 50s. And it's a link between the chain and the antichain in a poset. And that says that if you look at the largest antichain in a poset, then it's also equal to the number of chain you need to decompose your poset, the minimal number of chain you need to decompose your poset. That's, I mean, that has been used as probably something you all also know, everybody here knows about, and that has been used in many paper, many proof. It's also equivalent to Menger's theorem, for example, for people that do more graph theory, stuff like this. Yeah, and so it's very natural to ask, okay, such a thing is very useful. Can we have a strengthening of this? So let's use the definition that I just introduced before. Can we ask Dilworth theorem to use not just disjoint chain, but disjoint skipless chain? Okay, I don't know, do you have an opinion on this maybe? Or I can let you think a bit about it. So yeah, I guess the answer is kind of yes and no, but the main answer is no, in the sense that, well, you could still do something silly as just take skipless chain that contain one element for each element of your poset. That would be a set of skipless chain that decompose your poset, but you will never be able, I mean, there is some poset for which you will never be able to use as little chain as used in Dilworth's theorem. So for example, this poset, it has an antichain of size 2. It's a maximal antichain, for example, the 2 top element, but it can only decompose in at least 3 skipless chain, because one of the chain will use this 3 element, for example, and then you will use 2 different chain to cover the 2 last elements. I hope it's clear. Okay, so we cannot ask such a direct strengthening, which is not surprising, seeing as this theorem has been used so many times before. But what now if instead of viewing this poset as just a poset itself, we view it embedded in some Boolean lattice? So I just took a random, not a random, sorry. I just took some embedding, arbitrary one, here. And my question now is, okay, so we saw that we cannot just decompose this poset using two skipless chain. But now that we are in the Boolean lattice, in fact, there is some other element on the side, this 2,4 element. And thanks to this 2,4 element, we can find a cover using only two skipless chain of this poset. Okay. And it happens to be true for every poset and every way you want to embed it in the Boolean lattice. Okay. So that's just what's right in here, and that's our structural theorem. It can seem natural, but we'll see later that it implies quite a lot of things, strong things. So yeah, there's two ways of saying it. So how I presented it from the worst is just saying any subposet of the Boolean lattice, which has largest antichain of size k, can also be covered in the Boolean lattice by a family of disjoint skipless chain in the Boolean lattice. And one way to formulate it is just saying that any family of k chain in the Boolean lattice, just saying your subposets are just a family, not caring about the poset, can already be covered by a k disjoint skipless chain. Okay, so that's our structural theorems, and it's things like that have already been studied. So Lehmann and Ron first prove something similar, but which is the special case where all those chains have only two elements, and all the top elements are in the same layer of the Boolean lattice, and all of the bottom elements are in the same layer of the Boolean lattice. What I call a layer in the Boolean lattice is just some all the sets that have the same size. So layer T would be all the set of size T in the Boolean lattice. Okay. And then Dufus, Owa, and Leader prove later also another special case when the family is convex. We don't go into detail of what convex is, but just to mention those things, that there have been some studies about already the structural kind of theorem. And just to give you an intuition of what happens, so here you see some picture that represent what Lehmann and Ron proved. So what they proved is that something like this. For example, you have a matching, so chain of size 2, going from some layer here to some layer below. And you want to find a disjoint skipless chain that covers everything. Okay. And surprisingly, first, one thing that to get the intuition that this is not trivial to find such chains is that you cannot preserve the matching foundation, in the sense that it could be, well, you were lucky, the first chain, top element and the bottom element is the same that for the matching chain. But for the second chain, you could have to swap the source and target around, so the bottom and the top. So you already see that it's kind of tight in some way, like you cannot do whatever with your sources and your target that you want to get to. And you need to do something quite tricky. And actually what we prove to get to our main theorem that generalizes it to any family and not just to special family with top and bottom layer is just first prove some technical lemma that looks like the Lehmann and Ron with two more generalities. There's one element that you can put below, way below. Okay, so this element here is not in the same layers as the others. It could be way below. And also, you also enforce that there is some element in the middle that you want to keep. So you specify how those skipless chains are in these layers. And you want to say, okay, maybe you can swap which element goes into which chain, but you need to keep all those three elements here. Okay. And then it's a bit technical, but via a lot of double counting, a lot of application of Menger, a lot of induction, you finally manage to prove that you can have such a result that state that you can reorder your chain, find a new element here, such that they become skipless in this layer. Okay. And then you just need to apply this lemma a bunch of time, find some property of your chain family, such that you can always find some places where you apply this lemma and this reduced some quantity in a chain family until this quantity reaches 0. This is just very, very vague. I'm not trying to convince you that this is true. I'm just trying to give you I don't know, a taste of what the proof would look like, and also why it's not completely trivial that such a thing is true. Okay, so that's how you do it. Okay, is there any question now about the result? Because I will be using it later, and I just want to be sure that everything's clear. Okay, if there is no question, then I'll continue. Okay. So yeah, just to summarize, what we prove is that you can take any family covered by k-chain in the Boolean lattice, then you can just make those chain disjoints and still covering the same family. Okay, perfect. Now we'll jump to another topic and introduce some new notion. So it's about anti-chain saturation. So let's take a family. It's a extremal combinatorics problem. You're still in the Boolean lattice, and you look at a family in the Boolean lattice, and you say that it's k saturated if it does not contain any anti-chain of size k. But for any element of the Boolean lattice that you add to your family, then it's contain an anti-chain of size k. Okay, so it's saturated in the sense that, well, it still do not contain, but for anything that you add, it start containing. And you are interested in this extremal problem of what's the size of this, of a smallest family that is k saturated in 2 to the n, and you note it by this function sat nk. Okay, so maybe just a small example. If your poset, your hypercube is the hypercube of dimension 3, Boolean lattice of dimension 3, then you can see that this red family here is too saturated in the sense that it doesn't contain any anti-chain of size 2. But for any element that you add, it starts containing an anti-chain of size 2. It's quite easy to see because for any element that you add, it will be in the same layer with another element. So that will form an anti-chain of size 2. Yeah, and so this example just show that already that SAT32 is less than 4 because this family is of size 4. Okay. Can we extend this kind of silly example that just took a chain for the saturation family of size for being saturated for the anti-chain of size 2? Well, we kind of can, in the sense that if k is less than n, you can just take k minus 1 disjoint chain, and this will be saturated for the same reason, in the sense that if I add any other element in my poset, then it will be on the same layer as some k minus 1 element, which means that you would get an anti-chain of size k by just looking at this layer, because everything on the layer is incomparable. Okay. So this gives the following bound. You have k minus 1 chain. They're all disjoint, and they're all containing every element on the layer that are not the top layer and the bottom layer. So you have this n minus 1 times k minus 1, and you have the plus 2 because you both have the top set and the empty set. Well, that's a very basic construction. So people asked, is it optimal? Okay, so people start working on it and start proving that it's indeed the case, and it's indeed the optimal solution when k is very small. So for fixed values of k, k2, 3, and 4, and they conjecture that indeed it was roughly the optimal, in the sense that asymptotically it was of this form. And some more people later, a few years ago, continued this work. And interestingly, they proved that, okay, it was still this case for k equals 5. So you can just show that this formula above, if you apply it for k equals 5, this is for k minus 2. Okay, so this is fine. This is tight for k equals 5, but this is not the case for k equals 6. We have a minus 2 here that's not in this formula. Okay, so that's quite interesting. So you can do better when k is equals to 6, but still, they conjecture something even stronger than before. That's not just the asymptotic that is roughly the same, is that it's exactly the same up to some function of k. Okay? And in fact, I will try to convince you that this is there is a half a page proof of both this conjecture using our structural limits. Sorry. So the setup is like this. You consider some family that is k-saturated. Okay, you use Dilworth, you can get a chain decomposition of your family. It must use k-1 chain. This is just because you don't contain antichain of size k. Okay, and this family is it's saturated, so it's kind of maximal in the sense that if I want to add any element in my family, some y that is not in my family, well, I cannot complete a chain with this element, because otherwise, if I can add it to some of my chain, this means that I have a chain decomposition of size k-1. So I still don't have anti-chain of size k by Dilworth theorem again. Okay, so for any y in the Boolean lattice that I don't want to add to my family, it cannot be under some chain or in the middle of some chain. Okay. Well, now let's prove some very simple claim that just state that all the chain in my family need to start low enough and need to end high enough. And low enough and high enough are defined by this L function that is roughly, in fact, you can take L to be anything that is above such that k is less than L choose L over 2, roughly. So roughly L can be at least needs to be chosen of the order log k, roughly. Okay. So why such a statement is true? Well, let's suppose it's not, and consider some chain that end in a set X, and X is of size more than L. Then I state that I can always add some element to the chain and still have a chain decomposition of size k-1. Why is that so? Well, if I look at what happened between X and the empty set, well, what I have is, in fact, a sub-Boolean lattice, which is of dimension more than L, because X is of size more than L. So if I zoom in and I look just at the Boolean lattice that is in between X and the empty set, it looks something like this. And by the statement here that says that anything that could be added to my family, anything that is not in my family, sorry, would not be able to continue some chain. It means that everything in this sublattice need to be already in my family. Because if there was some gray element here, for example, it was not in my family, by adding it, I still don't create a new chain. I still have a chain decomposition using k-1 chain. And this implies that I still don't contain any anti-chain of size k. Okay. And I carefully chose L in order for this to be impossible, because I chose L such that this middle layer here of this sub-Boolean lattice contain at least k people. And I took my family is a k-1 chain decomposition, right? So it cannot contain k people on the same layer. So it cannot contain k people on this middle layer, which means that there is someone that is indeed not in my family, which is a contradiction. Hope it's clear. So this proved the lemma for just proving that we have some sets of size at most L, and for the set of size at least n minus L, this is exactly the same argument, but just do it above in the top of the poset. Okay, so we have such a claim. Let's sum it up and conclude quite quickly on these two conjectures. So we have a family that is k-saturated. We can take this decomposition by Dilworth, and applying the claim, we know that all the chain in the decomposition needs to start low enough and end high enough. Okay, now we can apply our theorem that says that, well, this family can also be covered by skipless disjoint chain now. But if you think about it, this family needs to be maximal. So if this covering is not exactly my family, if it's not exactly a partition, this would have meant that I had some element that I could have added to my family and still not contain an anti-chain of size k. Because in particular, if you have a k disjoint skipless chain, you have also k-1, sorry, disjoint skipless chain. You also have k-1 chain, full stop. So this means that you still have no anti-chain of size k. Okay, so yeah, what I was saying is that because my family is k-saturated, then discover is in fact a partition in this skipless chain. And now I just need to count, because what I have is skipless chains that are all disjoint and that contain n minus log k elements, thanks to the claim, in each of the chains. So I have at least n times k minus 1 minus some theta of k log k element in my family. And that's solving both of the conjecture. There was the first one was saying that the asymptotic was supposed to be n k minus 1, and the second one was stating that there is no second order term, it's just a function of k left and no function of n. Okay, so that's solving the two conjecture, and I think this gives you a glimpse of why this statement that can kind of seem natural in itself can still be very useful to prove interesting stuff. And actually, we started from this anti-chain problem and realized that we needed some kind of structure like this, and we saw Lehman and Ron result, and we said, okay, can we generalize this for this special case? We managed to generalize it, and then all the proof came true. But we didn't stop here, and we tried to get the exact value now, not just this asymptotic and this function of k. Let's try to get the exact value of what is the saturation number, the k saturation number. Okay, so what do we know for now? We know, well, the family needs to look like this, which means that we know that in the middle layer, we have a bunch of disjoint skipless chain, okay, nicely fitting. And for the top and the bottom layer, well, we're not sure. We have this example where we just continue this chain to be skipless, but we know that this is not always tight, for example, for k equals 6. And in fact, it has been proved that it's not tight for k great enough and n great enough compared to k. And you can, in fact, take smaller set in the top and lower level by just taking initial segment of collects. The idea is that, well, an intuition is that if you, I will go in detail of what I mean by initial segment of collects and everything later. But if you take an initial segment of collects, then you minimize the shadow, and thus you cannot continue this chain to go downwards. So you're already blocked, and you need only to continue a smaller number of chain downwards. And so you're using less and less elements. Okay, so that's just the rough idea. I'll try to go a bit more into details, but not too much. Yeah, so what I mean by shadow of some family that is included in a layer, and just look layer by layer now. It's just all the sets that are in relation to this family, but in the layer t minus 1. This family was in layer t, okay? And the initial segment of collects, well, that's the order that you see here. Roughly, is just like you want to, if you look at this order, you want to minimize the number of elements of the grounds that you're using. So at first, you look at sets of size 3, so you first use 1, 2, 3. But then, okay, you have no choice. You need to use 4, but then you don't want to use 5 yet. So you start, you put first the set 1, 3, 4, etc., etc. You can see it as minimizing the number of elements of the ground set that you're using while giving an order on all those set of size 3. Okay. And so why does it make sense to look at such a shadow and collects order for this saturation problem? Well, let's say that so that's what we have for now. We have this family that goes down, and at some point we have this k minus 1 element in this layer, and we try to construct the rest of the family to the empty set. Okay, so we have something like this. And Kruskal-Katona, a very famous theorem also, state that if you take the initial segment of collects, then it minimizes the size of the shadow. And that's kind of something that we want, because we want to be able to continue as least the least possible number of chain that we add at layer t. Okay, but actually this is not exactly what we need, right? Because this is not just about the size of the shadow. This is in fact a question about matching, because I also need to have those edges, right, to continue the chain. And we proved some statement that looks like Kruskal-Katona, but we didn't find any proof of this statement already. Maybe it's proven somewhere, but we didn't know. So if any of you know of this result already, we'll be very happy to hear about it. And so we proved that, in fact, if you want to also minimize the matching to the shadow, then you also need to take the initial segment of Codex. So no surprise, but we still need something like this. And why is it useful? You can see that in this example, even though the shadow is of size 5, well, if I want to continue my chain downwards, I can only continue 4 of them because my matching, maximal matching is of size 4. Okay, that's just to give you an intuition of why we care about this matching and not just about the size of the shadow. And interestingly, also the size of this matching is not just the size of the shadow. It's not as simple as this. So it's quite easy to see, for example, in this example, take all the set of size 3 that contain 1 up to 6, and you take 1 to 7. This is initial segment of Codex. And the shadow is one of all the sets that contain 1 up to 6 of size 2, and 1, 7, and 2, 7. And well, you can see that, of course, you cannot have edges to both 1, 7, and 2, 7 because they are only included in 1, 2, 7, right? And not included in the previous set. So only one of them will be matched in your complete matching, in your maximal matching, sorry. Okay, so that's just to give you a glimpse of what kind of theorem and lemma you need to complete this chain in the base of your poset in the lower level. And surprisingly, I will explain why it's surprising a bit later in the talk. We managed to get the exact value for this saturation number on a very mild condition on n. We want n to be of size at least 2L plus 1. So if you don't remember what L is, it's not that big of a deal. Just rate it as log k. So we just want n to be more than 2 log k. Okay, so that's very mild condition. And for any of those L and any of those k, then we have this exact statement. And roughly this part here that is nice is just use k minus 1 chain in the middle layers. And this part here is just summing over. So first you have the maximum matching from the initial segment of Codex of size k minus 1. And then the maximum matching from this initial segment of this size going downwards, etc., etc. This is defined recursively like this. So you take maximum matching, then maximum matching from, again, below and below and below until you reach just the empty set. And this is in fact optimal. So what I show you a glimpse of just before is how to prove the lower bound. So this part of the lower bound for the lower levels. And in fact, of course, the top level works the same. So that's why you get a factor 2 here. But it's why do we need this mild condition? Yeah, maybe I will show you. I don't have a picture to show you, sorry. It's just because we have this weird thing happening for the top and the bottom of our Boolean lattice. And well, when the top and the bottom got too close, we also need to find those chain, right? Linking the top to the bottom. That's what we call nice middle layers that were just filling up by some set of size k minus 1 each time. We just take k minus 1 of the set. Well, if the top and the bottom got too close, it's kind of hard to find the matching in between them, right? Because you still want to find matching because what you want to construct is a chain, right? So still, like there is some more difficulty when you are in these cases, and it's still an open question. It would be nice to have a more general construction that works perfectly for all n and all k and settles the problem. Okay, and just to give a very quick glimpse, there is way too much text on this picture on this slide. Try to not read it, please. It's just to say that for the upper bound construction, I told you that the initial segment of Codex was very fine. It was minimizing the matching and everything. But still, for the upper bound construction, you cannot use the initial segment of Codex, which is also quite surprising. You need to do something a bit more technical. This is mainly due to K being not exactly this L choose L over 2 that I'm considering. So you need some induction inductive construction that's just rely on some nice decomposition of k-1 into a binomial coefficient. And interestingly, for those who know, this kind of decomposition are quite often used, for example, in Kruskal-Katona. Here, it's not exactly the same decomposition, so that's quite interesting. But yeah, nothing, no breaking news here. But yeah, you need to do something more even for the upper bound. Okay, so that's it for the anti-chain saturation. And now I want to go into the other paper that's also talking about general saturation, but saturation, I mean, but in a more general context. So this anti-chain saturation thing, we can also define it for any poset, actually. So if I take a poset P in also staying in the, sorry, I take a poset P, I take a family F in the Boolean lattice of dimension N, and I want it to be P saturated if it does not, oh, sorry, there is a knot that is missing here. F has no copy, no induced copy of P. But if I add an element X in F, then it has an induced copy of P. Okay. And I emphasize on induced, and when I say copy now, it will always be induced. So if you change P by the anti-chain of size K, this is exactly what they called K saturated before. Okay. So one of the first theorem on this setting is actually by Moissan, Noel, and Scott that proved that, well, if you look at the chain of size K, which is maybe the most simple poset and the first poset you asked the question on, then this saturation number is bounded in between this value, this 2 to the 0.98K. And there's another result before that also proved the lower bound, but the lower bound is quite worse in the sense that it was still, that's quite surprising. When I say that we were surprised to have an exact value, is because even in this simple case of the chain, which could seem like the simplest poset you could look at with the anti-chain actually, probably, well, we still don't know the exact value, and there is quite a huge gap. We still know that it's independent in n. This is a constant, but we still don't know exactly what's the value of this constant for any n and k actually, except for very small value of n and k. Okay. Yeah. And well, this has been studied for a lot of posets, so do not read this slide. Also, it's just to show that there is a lot of poset. On the right, you get the poset that has been studied, and on the on the left, you get the poset, and on the right, you get the bounds that have been proven. It's not completely up to date. It's just to show that, well, it has been extensively studied for small poset and some infinite family of poset, which roughly are the chain, the anti-chain, and some very weird family. Okay, but before very recently, there was almost no results that apply for any poset P. And just actually this year, it has been published this year, there is a first interesting, quote unquote interesting, general bound that have been proven for this poset saturation. And it shows that either you are constant or you are at least square root n. And that's quite surprising. The proof is also very nice. And well, we saw this result and we were like, could we ask the same thing for a general upper bound? Is it possible? Because we are on the Boolean lattice. So technically there is 2 to the n elements. Is it possible that the saturation number of some poset is 2 to the square root n or any weird function of n? Or is it also bounded by maybe some polynomial or something? And it is, actually. We proved that there is always a polynomial function depending on P that bound this saturation number. So this saturated family, even the smallest was, is always quite sparse. Okay, and you can put P to size of P squared here if you want. That's roughly the best that we can prove. And to get this result, we also needed to define a new parameter on poset parameter that might be of interest in themselves, because we only need very mild result on this parameter to conclude our proof. but it could be that we could improve something directly here. So let me introduce those parameters first. We define the cube height to be the minimal integer h, such that you can find a copy of your poset P in the first h layer of an hypercube of dimension high enough. So this n could be any n. You take a very big hypercube, and now you try to embed your poset as low as possible using the minimum number of elements for each of the set that does the copy of P. Okay, and once you define this cube height, now you define the cube width, which is a bit more technical. So you look at this minimal way to embed the poset using the minimal height, so using the cube height, and now you try to reduce the dimension of your poset. So your width will be the minimal dimension of your posets, such that you can still embed it as the minimal height to which it can be embedded in any any Boolean lattice of any dimension. Okay, hope it's kind of clear. If it's not, just forget about the definition and just, yeah, maybe some example before I am too discouraged to get you the intuition of this. So if I look at the antichain of size 5, well, it can be embedded like this. So this, you can see this as just the bottom part of some Boolean lattice. And if this is also the minimum height at which it can be embedded, because of course it contains more than one element, so it cannot embed it in the Boolean lattice of dimension 0. And okay, so it needs to be embedded in layer 1, and it needs to have width 5, because each of these elements would be a single, right? So this is just the first 2 layers of the Boolean lattice of dimension 5. Well, okay, so this means that the cube height and of the antichain of size 5 is 1, and the cube width of the antichain of size 5 is 5, okay? And why does this condition of being embedded in the minimal height matters? Is because if I was more lenient and I could embed in any height that I want, then I could just take the first 3 layers of the Boolean lattice of dimension 4 and have a copy of the antichain of size 5 here, right? So that's 1 dimension less than the cube width of the antichain of size 5. So this is not completely trivial to compute those cube height and cube width. And this is not always, of course, the same as the height and the width of a poset for those who know the usual definition of height and width. Okay. Just to give you a glimpse of why those definitions are useful and how do you prove a polynomial upper bound. It's a construction proof. So I will just describe to you a way to construct a family that has this size and it's also saturated for P. So first, let's do something very silly. I just take all the bottom layers and think I cannot take the layer completely. So this is my F0 here. I just take all the bottom layers until, well, there is some element in the layer H plus 1, for which if I add this element, then it creates a copy of P, okay? And you can see that, well, the number of layers that I take is in fact this hypercube height, right? Because that's -1. Because what I'm saying is that I take all the layers before I can embed my poset, right? And the height was defined as at the smallest number of layers I need to take such that I can embed my poset for some large enough n. So if n is large enough, and we always look at n to the infinity, then this is only the first hypercube height, -1 layer. Yeah, and it's described like this because you also have the layer 0 here. The -1 plus 1 doesn't really matter. And F1 is in fact any completion of this. So one thing that is nice to see is that if I give you a family and it's P3, which means that it doesn't contain any induced copy of P, then you can always construct a P-saturated family by just going over all the elements that are left in your Boolean lattice and just add them when they don't create a new copy of P, right? If I do that, I go over all the elements like this. What I have in the end is a family that contains my first family and that now is P saturated, because if there is some element that I didn't add, it means that it would have created a copy of P, right? So what I say here by any completion is just I go over the element in any order and just complete it, okay? And the key lemma is that this completion always have bounded VC dimension, in fact. And I won't go into detail of why, but the idea is that if we shatter a large enough set in this set F1, well, roughly it means that we have all kind of correlation to this bottom bit F0. And if you have too many kind of relation to the bottom bit F0, well, roughly you could find your copy of P, because you just embed almost everything of your poset in F0, and then for the maximal element, you just choose the right relation that compares to your embedding, and you're fine. That's also quite a short proof, just to give you the intuition. And so this is a very nice construction also, because it's very easy to compute, right? For you just take the first layer and then you go over it and just ask, does it create a copy of P or not? So yeah, you can create this family in a time polynomial in the size of the hypercube, which I don't know, if you do a bit of computer science, could be useful for, I don't know why. Okay, so what we prove with this is in fact that the VC dimension of this family F1 is bounded by the width now. So the first family was bounded by the height, the first layer, and the width bound the VC dimension of the family above. And as you probably know, Savard-Scholler lemma tells you that if a family has bounded VC dimension, then it's not too big. And so we can have this bound that says that this is polynomial in the width of our poset -1. And now it's what left to be done is just to bound this width. And we just found some silly bounds. So it's very easy to see that the height of a poset is atmos P, just for very well-known result that any poset of size n can be embedded in the hypercube of size n. So in particular, it doesn't use more than height n. Okay. And the width is at most P times the size times the height. That's just because if your height is low, I mean, whatever your height is, let's say h, then all your elements contain at most h element of the ground set, right? So you need at most h times size of P element in your ground sets, and your ground set is your width, right? So you get this P squared upper bound. But it's not at all trivial that this is optimal. So I guess for h, we prove that it's probably already known, but that you have some posets that for which the height is P-1, actually, and that's optimal. And for the width, we still don't know what kind of best upper bound we could have. It could be linear, actually. We still don't know. Okay, and we in fact improve it a bit more with some ideas that came from the lower bound ideas, actually, and we got just a bit better bound by just a factor of 4. That is still quadratic. Yeah, and that's it for our result. And I will try to take a few minutes. I have still a few minutes to just tell you about some conjecture that I like and why we still don't know anything about poset saturation, even though I'm talking about it for an hour. So yeah, the first conjecture is what I was talking about, that maybe this width parameter is in fact just linear in P. We asked a few people doing poset theory, and it seems that this width parameter have not been studied yet. So it's still completely open. And this will directly improve our upper bound, because our upper bound depends on this width parameter. And maybe my favorite conjecture on this topic is a very strong conjecture that says, okay, you prove that either you're constant or you're more than square root 10. And now we just prove that you are always some polynomial. But what if, in fact, you can only be of two types? You can either be constant or be polynomial. And something that's crazy is that you saw this table with, I don't know, maybe 20 or more, 40 posets, and none of them is a contradiction to this conjecture, right? So it could be that this conjecture is true, but we are still very far from proving anything like this. But that's a very nice conjecture, and I would be very happy to see a counterexample, and even more happy to see a proof. And one very last, it's not a conjecture, but it's just to give you a glimpse of how little we understand about this poset saturation, is this thing. If you take a C2, well, the saturation number is 2. It's just because you can take the empty set, for example. That's a set of size 1, sorry. Saturation number is 1. And anything that you add is below the empty set by definition. So saturation number is 1. If you look at 2 chain, well, you can prove, this is a paper, it's not too difficult, but still need a proof, that actually the saturation number is linear. But now if you take 3 chain of size 2, it's constant again. And I think this is crazy. It just shows that we don't know anything that works in general for all posets. We know very, very few things. And I kind of like this example. I think it encapsulates everything we don't know about these parameters. And that's it for me. Thanks a lot for listening.
Okay, thank you very much. Lovely talk. So please do feel free to unmute yourself and ask questions, or ask questions in the chat. Actually, I have a couple of questions. So one is there any conjecture for which posets have constant saturation number? Is there any?
That's a good question. No, it's not known. And there is also the more computer sciencey question of, is it decidable, or what's the complexity of deciding if it's constant or if it's linear or more or something. So it's widely open, and I think there is a lot of things to do before reaching a complete characterization for this kind of thing. Yeah.
Okay, and another thing I wanted to ask about. So your width parameter, you kind of you squash it that way first and then that way.
Exactly. Yeah.
Did it the other way around? Does anything interesting happen?
If you do it the other way around, both parameters become linear, just because, well, that's roughly because you are embedded in the hypercube of dimension n. So you can always do it with width n, and then, well, the number of layers you need is at most n, right? But this is, I don't see how we could use it in our proof. Like, it really came in the other direction in our proof, so that's why we define it in this way. But maybe if you can see it in the other way and make it worse, this would mean a better upper bound if we could swap the definition.
Okay, thank you. Would anyone else like to ask a question? Okay, in that case, let me invite everyone to stop the recording, and then invite everyone to unmute yourselves and express our appreciation for a lovely talk.
Thanks a lot.